Yo, welcome back to another Professor Sykes video. Today we're going to be looking at energy which is a physics topic. So my revision schedule has changed, so that is why I'm not doing a biology video and why I've not done one since last Thursday. But with that out of the way, let's get back to the video. So the first thing that we're looking at is the energy stores and pathways. So energy can be stored and it can be transferred between pathways. So you've got several pathways. You've got the thermal store, which is how much heat an object has. You've got the kinetic store, which is how much movement energy something has. So my pen moving across the screen now, I take energy out of my chemical store, which is another one from the food that I've eaten, and my muscles use the chemical store, transfer it into kinetic energy, and they move, and that gives the pen kinetic energy, because it moves with my arms. There's also gravitational potential energy and elastical potential energy. These two are stores of energy. So gravitational is how high something is, and elastic potential is how much how stretched it is and how much energy is stored in the tensile object that you're stretching. There's chemical, there's magnetic, which is how much energy is in the magnetic field lines. There's electrostatic, which is how much is stored in your ionic bonding and things like that, which is quite important in the chemistry topics, but not so much in physics. And there's also nuclear energy as well. So that's how much energy is stored in a radioactive element, which it then gives off as subatomic particles and gamma radiation, which is an energy wave. So there are four pathways because you need for energy to travel from one store to another, you need to use a pathway to transfer it. So there's mechanical, so that would be me physically lifting the pen from the paper to a higher height. So that gives it more gravitational potential energy, and then I move my fingers and it drops, and obviously you can't see very well because it's too fast, but I drop it, and the force that I've put in and the force that gravity puts in causes the pen to change energy from gravitational potential to kinetic. There's also the electrical pathway. So you run a current through something. That would be something like you're going from a chemical store to and one of the other stores. You can also heat something, so that would be more likely a chemical to a thermal store. And you can also, well, we can't, but an atom could also or an object could radiate something. So your gamma rays, your subatomic particles, or it could be it radiates, light, which is similar in many ways to gamma radiation. It could be emitting sound as well, just emitting some kind of radiation. So, as part of this topic, let's look at kinetic and potential energy specifically. So, kinetic energy is how much energy something has while it's moving, and it can be found using this equation here. So you do a half times the mass times the velocity squared. So if I had a 1 kilogram object moving at 5 meters per second, I do a half times 1 times 5 squared. So that would be a half times 1 times 25. So that would be a half times 25, which is 12.5 joules, which is the unit of energy. There's also gravitational potential energy is how much energy an object has when it's lifted away from the ground. So to find that, use this formula here. M is mass, G is the gravitational field strength, which it will tell you on the exam question, but if it doesn't for some weird reason, you should always assume it to be something along the lines of 9.8 newtons per kilogram, I think it is. so that's Earth's gravitational field strength. Obviously, if you were using this calculation on a different planet, the gravitational field strength would be different, because every planet, unless it was an identical size and density to Earth, would have a different gravitational field strength. And your the height from the ground is represented by h. So if I had a 1 kilogram ball and I lifted it 10 meters from the ground level, and I'm on Earth, obviously, so then I'd do 1 times 9.8 times 10, so that would be 98 joules. So that is your gravitational potential energy. So when something with gravitational potential energy drops, it's transferring from the potential energy to the kinetic store. So that's what's happening when that. If you imagine it kind of like you have two kind of bars. This is gravitational and this is kinetic. As it's falling, gradually it kind of shifts out, and then it's at the top. And then when it hits the ground, its kinetic store will increase, and then if you kind of imagine shifting it along, your sound, the sound would be released. So I'm not sure which one that would be. Possibly kinetic again, but a different store of it. But you'd also have some kind of thermal energy being lost as it's falling because of air resistance. So those stores would increase while it was falling and as it hit the ground, whatever you dropped. An elastic potential energy is when you stretch something or when you squash something. So if I had an elastic band, I do actually, bear with me. So if I were to use this as an example, this is an elastic thing. I'll just actually, hold on. Right. So this is an elastic object. When I stretch it like that, it has a high elastic potential energy. And then when I let go, the elastic potential energy is gone because it's transferred into the kinetic store and the various other ones as well. So you can find it using this equation, and that is a half times the constant. So every spring has a constant, which is the kind of how easy it is almost to stretch it. So that one would have the elastic binding around my book would have a relatively low spring constant, I imagine. But if you think about kind of your industrial springs that they use in a lot of your kind of things like washing machines that have springs in and other machinery, they would have a higher constant, because they wouldn't want to, because with a low one it wouldn't support the weight of whatever they're meant to be holding up. Now this E is the extension as well. So if I had a spring and I extended it 2 meters, and it has a spring constant of 2 newtons per meter, I think that's the unit. So it would be a half times 2 times 2 squared. So it would be 1 times 4. So that would just be 4 joules of energy in that. So let's go on to the next thing. So the next thing is called specific heat capacity. So this is basically how hard it is to heat something. So it's how much energy a substance needs to heat itself by 1 degree centigrade for 1 kilogram of that substance. And it's a specific property. So the specific heat capacity, that's why it's called specific heat capacity, because the specific heat capacity of water would be different to that of copper, and that would be in turn different to that of sodium or whatever. Every single thing has a different specific heat capacity. It's like boiling and melting points. And you can find the energy transferred to an object using this. So E is your energy, M is your mass, C is the specific heat capacity, and this sign is theta, and that means temperature. And when you see a little triangle, that's delta, and delta symbolizes a change in. So the change in energy is the mass times the specific heat capacity times the change in temperature. So if I have a 1 kilogram block of water, it wouldn't be a block then, would it? If I have a 1 kilogram block container, for goodness sake, a 1 kilogram container of water, and I heat that up by 5 degrees centigrade, then it would be 1, because of the mass, times, I think the specific heat capacity is 4,200 joules per kilogram. So it would be 1 times 4,200, and then it would be times 5. So that would be 21,000 joules of energy transferred. But you can also use this to find, you can use this equation, rearrange it, to find the specific heat capacity of a substance. So you'd use this practical setup here. You'd have a power supply plugged into mains, most likely, but it could be running on batteries, don't know. You plug that into an ammeter here, and you plug that into a heater, and then you plug the heater back into the power supply to complete the circuit. You also need a stopwatch, and you put a thermometer in a different hole in the block of metal that you're using. And you want to, so in this experiment you're trying to find the specific heat capacity of a metal. So you put the heater in one hole in the metal, and you put a thermometer in another, and you want to wrap a piece of insulation, which is represented by this dark bit on it. You wrap a piece of insulation around it, so it could be some layers of cardboard, or it could be some layers of cotton wool, which I wouldn't advise because that can get a bit messy, to be honest, especially if you're using water instead of a metal block. But also what I would advise doing is putting a very slight amount of water into the hole where the thermometer and the heater are, because otherwise you might end up scorching the block, or the energy might not properly transfer into the block, or it could even be the case that the water would act as a slight coolant as well. So you might find that it would set on fire, say, in some extreme examples. So what you want to do is you want to set the power supply to a set voltage, so say 10 volts, and then you measure the current on your ammeter, and you measure the change in temperature on your thermometer. So using a different equation, which we're going to look at in another physics topic, you know that power is voltage times current. So if you've got a 10 volt potential difference, and you've got, say, a 2 amp current, so your power is 20 watts. Now I'll touch on this in a bit, but watts is joules per second. So power is energy over time. So to get the energy, because you need the energy for the specific heat capacity, you do your, what did we say, 20 watts that we found times the time that it's on. So say it's on for 30 seconds. Your energy is 20 times 30, so that is 600. So you've transferred 600 joules of energy. Now, then you substitute it back into the specific heat capacity equation. So 600 equals, say it's a 1 kilogram block, 1 times x, because you don't know the specific heat capacity, that's what you're trying to find, times, I think we said it changes by 5 degrees. So, or if I didn't, let's just say that now. So it would be 600 is 1 times x times 5. So you divide by 1, so 600 is x times 5. Then you divide by 5, so you would it'd be 600 over 5 is x. So the specific heat capacity of this specific substance would be 120 joules per kilogram per degree centigrade, which is the unit that specific heat capacity is in. So let's go on to the final bit. So talking about conservation of energy. So energy cannot be created or destroyed. It can only be transferred or stored. This is one of the most fundamental beliefs almost in physics. So you've got to have this stuck in your head. You can't just go around creating energy. Even power plants don't do that. They generate electricity. They transfer it from the fossil fuels or whatever you're using as a fuel source into electrical energy, which is a charge flowing and carrying negative electrons that do that, which I'll cover in a separate topic. But you can't create or destroy energy. So, but you might notice in some of your experiments that some of the energy isn't transferred where you want it. So you might, I don't know, be measuring the specific heat capacity of water, and you might find that the energy transferred isn't quite enough so that the specific heat capacity is 4,200 joules per kilogram per degree centigrade. You might not find that. The reason is that there are always, in every application, energy is wasted. So this would mean that your energy would, some of the heat could be transferred to the air, some could be transferred to the water and not into the metal in this one. You could have resistance along the wires as well, so that would mean that the wires would be heated rather than the actual heater. There is always some energy wasted. A closed system, however, means that no energy escapes. So I said about systems before, a closed system means that no energy escapes from that, so it would be something like a reversible reaction where the same amount of atoms are in there. A true closed system is very hard to obtain, but a closed system is where no energy escapes, but there could still be energy wasted in there. Now I said I was going to talk about power as well. So your power is, you'll often notice that bulbs have a power rating. So the lamp that I'm going to turn on now because it's getting a bit dark has a power rating of 9 watts. Sorry about you guys out there who I've just blinded. But this lamp has a power rating of 9 watts. So that means every second that it's on, it transfers 9 joules of energy. And you can find the power using these equations. And in this it shows that energy is equivalent to work done, which are both related to, well, work done in particular is related to other topics. So I hope that was helpful. More will be on the way very shortly. So that's it for this video. So good night and God bless.